And some additional work, if you had read the other papers, this you would have read this. We came up with a model for oxygen availability. This is a pellet form of A Niger. Pellet is a condensed form without the hyphae sticking out and so on and so forth. This form is needed for production of certain products. So, we considered this as a sphere, we considered a shell here, did shell balances. If you do not follow the details, do not worry too much about it. If you have not done transport, you may not follow it completely. Shell balances, and then we came up with material balance models for this is a pellet of A Niger with just the hydrogen peroxide. This is when aeration is used, you will have this relationship for the oxygen concentration. And when hydrogen peroxide is used, the oxygen profile will turn out to be like this. The reaction rate is given through various different literature information. We got this expression for the Ra here, the reaction term here. And the results can be summarized to a certain extent like this. When you consider aeration, this is the pellet radius. Okay. So, this is a 1 mm diameter pellet, 1 mm diameter pellet, and this is a 2 mm diameter pellet. The oxygen concentration in millimolar, as expected when you use aeration, where oxygen is available only in the surface it's quite high, drops to 0 in about 0.2 mm. So, this part of the pellet is completely devoid of oxygen, whereas here it drops to 0 quite early, 0.85, sorry, 0.8 something, 0.8, 8 and so on and so forth. So, most of the pellet is anaerobic. Okay. So, if the productivity depends on oxygen availability, then it is going to be a problem with these things. Whereas, when you use LPOs, just the reverse happens. You have the center having the highest oxygen levels, and it drops to 0 because you are using only hydrogen peroxide here, drops to 0 at the surfaces. So, the entire pellet is oxygenated. Yeah, it's it's a cell. It's a cell without the hyphae. It's a different form of Aspergillus niger, right? So, you can imagine a mushy kind of a thing there. So, you have I mean, this was good insight into the oxygen availability and so on. We also did optimization on the macro level. This work was done by Chaitali, I think, yeah, Chaitali. So, we essentially wrote balances. This is hydrogen peroxide in the intercellular space, cell concentration, product concentration, glucose concentration, nitrogen source concentration, and this is just the volume, right, volume and flow rate and so on and so forth. Essentially balances, mass balances with the focus on that on our system. That is all we did. If you do not follow the details, do not worry too much about it. And then the co-guide for Chaitali was Ravindra Gudi. He was into bioreactor operation by different optimization strategies. So, he came up with an optimization strategy using these dynamic equations, and then there was a further 50% increase in productivity of xanthangum. Chaitali worked on xanthangum, further 50% increase, which is published in Biotech Progress, which is the second most reputed journal in our field according to me. The numbers, I mean, once the numbers came in, it's a different story, but I still go by these things. I'm not way off, but that's okay. This is not in the papers, but what about the cost of hydrogen peroxide? Because it is in the paper. Oh, okay, fine. It may not be the detail. Because no paper would take this much amount of detail. So, we looked at the cost of hydrogen peroxide, 50% weight per volume solution, which is available in bulk. Okay. The reagent grade is of course far more expensive. We do not need reagent grade. Okay. National Peroxide was the company that was producing it at that time. That was 14 rupees per liter. I checked the cost during the pandemic, it went up to 35 or something like that. and then now, about a year ago, it was still 29 and things like that. Not too much, but you can figure out the various things. The cost of 1 kg is 28 because 1 kg of hydrogen peroxide is a 50% weight per volume solution. This is the reaction of interest, and so 2 moles of hydrogen peroxide give you 1 mole of oxygen, and in terms of masses, 68 grams of hydrogen peroxide gives you 32 grams of oxygen. Or you could calculate that 1 kg of oxygen requires 2.125 kg of hydrogen peroxide, and therefore the cost of 1 kg of oxygen generated from hydrogen peroxide, if you don't consider anything else, is 59 rupees 50 paise. Okay. The cost of 1 kg of oxygen from air through filtration, compression, filtration, and so on and so forth was about 2 rupees per kg at that time, right? However, as you already, if you've seen the paper, you know the story. The effective cost is much less because you'll have to compare it on an appropriate basis. You cannot compare it on a kilogram of oxygen basis. That, of course, is very different. But what is the oxygen used for should be the basis for comparison. For that, you need to consider these facts. The productivity is higher with LPOS. The power input required to maintain a high KLA, which is required while using sparging to provide oxygen, is about 20 times, 20-fold the power input required for reasonable mixing. Okay. This is well understood in terms of correlations and so on and so forth. So, this, when aeration is used, only a small fraction of oxygen that is generated, which is entering the bioreactor through air, gets actually utilized. Only 3% gets utilized, or rather 3% of the 21% gets utilized, 18% actually goes out. We have done the measurements. Okay. The rest is lost. The sterilization and handling of the air supply system is difficult and leads to loss of whole batches due to contamination. This has come down significantly, but still it happens. If you go to the industry and ask, we lost a batch, kind of thing. And in addition, no anti-foam costs are involved while using the LPOS. There are no major scale-up issue. It's only mixing. It is not a major scale-up compared to KLA and all that. And residual hydrogen peroxide is not a problem. There were statements only on the residual hydrogen peroxide, even in the US FDA guidelines. There is no hydrogen peroxide left. It's all gone. It gets broken down very quickly. Therefore, that is not a concern. So, if you consider even the first 4, we have some time. The productivity is higher on the average by about 2.5-fold. If you take that, the effective cost comes down. Lower power requirement, you take that, it comes down on the same power input basis, comes down to 1.19, which is already less than 2 rupees per kg. Consider a couple more. Better utilization, you consider that, it comes down to 0.143. And sorry, 3 by 21 is 0.143, the cost comes down to 17 paise. And then air handling system not being required now, you don't need an air system at all. And it comes to 15 paise. So, even then at that time it was 15 paise versus 2 rupees. It was also economically advantageous, significantly advantageous. In addition, we have not considered these for the costing. No anti-foam, batch times are less, no major scale-up issues, no FDA difficulty with residual hydrogen peroxide and so on and so forth. So, it seemed advantageous. Okay. So, did we solve the problem? Of course, we did. Okay. However, in science, as with anything in science, you solve something, you raise 3 more questions or many more questions. Okay. That's the way, that's the hallmark of doing good science. What we found was that reactive species, especially reactive oxygen species, are important. Okay. I presented only the rosy picture. I didn't present the gory picture. Okay. The gory picture was the ROS were responsible for the gory part of the picture, which I will take up next. Before that, something related. This is Pritish's work, Pritish Sarkar's work. You have you add hydrogen peroxide, right? The concentration here in the addition zone is going to be much higher. Therefore, that is going to lead to loss of toxicity and therefore loss of cells in culture. Yeah, there is mixing and all that, but the practical aspects of mixing. Pardon? Yeah, definitely. Yeah, that is what we are coming to next. I'm not taking it up now. Yeah, taking it up partly now. So this leads to, yeah, this is my story. Okay, this leads to a reduction in the maximum cell concentration as well as the growth rate. Growth rate to a certain extent, definitely in the maximum cell concentration. This is with aeration. This is with LPOS. It's about half. Okay. So I got greedy as any engineer would. So I said, if I can increase this to here, then the productivity goes that much more. So how do I go about doing this? The reason for the reduction seems to be reactive oxygen species. So how do we handle the reactive oxygen species so that while using LPOS, the cell productivity also becomes high? Was the reason for us to get into reactive species. Then it consumed us totally. We have been in that for the past 3 decades and continue to be there. Okay. We actually didn't do this experiment for a long time because there were so many interesting avenues that opened up for investigation. We were very busy with that. And for some reason, much later, I think 2 or 3 years later, we actually did the experiment and we use the data differently, which probably I'll talk about. Okay. One of Manjula's papers has that data. We'll talk about. So when Manjula joined, Manjula was my first PhD student. I think I've already told you her story, some part of her story. So her question, she already had some background in reactive oxygen species with mice and so on. So that's the reason why she was interested. She was only although she was the only student who joined at that time PhD, she agreed to work on this. And the first question was, I presented the thing to her. We were thinking about how to handle ROS. She said, can we vaccinate against the reactive species effects? Right. And that is the starting point of our future work into reactive species. So I don't think I'll mention this here. If you don't have enough oxygen, it is hypoxia. We have also looked at it's not very appropriate for the story to mention this here. I will certainly mention this partly. This work is being done by Sonal. She is yet to graduate. She's finished her experiment. She's for the analysis part. She's completing her work and she's writing a thesis. Pardon? Cells is cultivated, right? Yeah. Cultivating cells. The number of cell counts is more during hypoxia. It was given like that. Cell count increased. Which paper? When we are not administering. Which paper? In the first one, the first paper. Actually, during hypoxia. But the production of xanthan won't be there. Xanthan production will be this. I'll figure out where did I mention hypoxia there? Not hypoxia, but lesser oxygen conditions, yes. Hypoxia is very low. We don't administer H2O2 and only regular aeration. Yeah. During that time, the multiplication of cells will be. Yeah, that is what this data tells you. This is exactly what that data tells you. So this is with the solid circles are with LPOS and the open circles are with aeration. So this was the reason why we got into reactive species research because we knew that reactive oxygen species was causing this drop. Hypoxia is different. Hypoxia, this is not enough oxygen, but it is being provided at a reasonable rate and so on. Less oxygen condition. Whereas hypoxia is about 1% or so. In the body, there are many niches, especially where stem cells reside and so on and so forth, where the oxygen tension is very low, about 1% and so on and so forth. There, it so happens that there's a good reactive oxygen species relationship to them also.
After studying this, I thought, okay, RO species will prevent excess proliferation.
Depends on the system. Yeah, it depends on the system. If you're looking at a production system, we don't know. We did our studies with mammalian cells, with cancer cells, in fact, hypoxia. That I'll probably just mention towards the end because the work is still not complete. I need to look at it from a different perspective to mention it in a class and so on. Research perspective I can mention. Okay, I think that's where I'll stop here. So just ignore the last one. I thought at that point in time my story was this. Then I changed the story when I was writing the book. So let's not worry too much about that. Okay, and questions, comments.
One point in the paper, the volume of H2S, I mean H2O to the 30%.
No, less than that. No, 12 ml out, 24 ml out of a liter, which is insignificant. So, we didn't want to arrive at a situation where whatever you add increases the volume of your reactor too much. It will lead to dilution and other unnecessary things while operation. So, we didn't want that, and if you used the concentrations we used, I think we used 30%. Yeah, no, it's a concentrated solution. H2O2, required H2O2 is provided. Only thing is that it's provided in a lower volume, but it will cause difficulties like this. The concentration here in the feed zone will be very high, so the toxicity will be high.
Is there any other way of adding differences where it's not concentrated?
Yeah, various things. You could take it, you could generate it separately and add it and so on. So a lot of these thoughts. Yeah. We have thought about it. We've done some experiments also on that. All these have been explored, but I don't know. No, we didn't publish them. We certainly didn't publish them. There is enough scope for that. This is about 30 years old, so you might want to think about it. If you want to leave, please do. If you're going for the next class and so on. And I think we need to stop. Yeah, this is a course, so we'll stop here. What we'll do is, if you have other questions, we can discuss separately if you have individual questions, or before we get into the next week's thing, we will first discuss this and go forward if you have those questions then. Next, we're not going to have a class. Tomorrow is a holiday, it happens to be a holiday. The next time you'll have a larger number of papers to read, I think 4 papers. So Monday is off. You'll have time to read on Friday as part of this, plus Monday, typically 2 days. And then the next class is on Thursday. There will be an incentive quiz and we'll discuss that aspect. Okay. Or should we continue to discuss this on Monday and then we can continue to discuss this on Monday, right? Yeah. But yeah, since there is an interest, we'll discuss this on Monday. Please come to class on Monday. We'll discuss this. You'll have time over the weekend as well as Monday to read those papers, and Thursday we'll have the incentive and so on. Okay. I've already opened that up for you. You have about 4 papers. See you people.